Hello everyone. Indeed, my affiliation is NTNU Business School, and the second affiliation I would like to mention the University of St. Gallen, because part of the results I'm presenting today will refer to my work in both placements. So I would like first to thank the organizers for the invitation to this very nice program. I had a wonderful academic exchange over the last 2 months, and especially I could deepen my knowledge into modeling the intraday electricity prices. I was asked by the organizers to focus on the intraday electricity prices. My research track included day ahead and also futures markets. So in the limit of my time, I'm also going to give you a resume of what happened during our discussions. Okay. So I thought about giving you an overview of the research needs and the knowledge needs for energy industry firms concerning the intraday markets. Afterwards, I'm going to focus very much on the patterns, the identification of the patterns in prices and volumes in the intraday markets. You will see it's a crucial step before proceeding with any modeling approach. Afterwards, I will present you some of the models I developed myself in my own research, and in the limit of my time, I'm going to show you which research topics emerged in this research track. So the energy firms actually need to learn more and more about what trading strategies they should use in the intraday market. Why? Because we are in the middle of market coupling. Markets connect, energy markets interconnect more and more, which means we witness bottlenecks to aviation areas with different price levels. And the major challenge is to balance out renewable energy sources. So this is a key word linked to why we need to trade in the intraday markets. So the current trends and needs, at least in Norway with the industry partners I'm collaborating, is to move towards an automatic intraday trading, because the state of the art is that the trading in intraday markets is done still manually, which is very costly, and so the goal is to identify trading strategies based on a rigorous identification, obviously, of the demand supply factors in the country itself and in the interconnected markets as well. And the final goal is to move towards high value trading. What do we understand under that? We want to find an optimal intraday timing and volume to be placed in the continuous bidding process, and to explore as much as possible which information is incorporated in the price bids submitted in this continuous bidding system. To achieve this, however, there's one first step, very, very important, which I will especially address today. We need accurate forecasts. We need accurate forecasts, first of all, of intraday prices and the volumes. And there are essentially two approaches in the literature to deal with this. First one is to link, and I'm going to focus on this, to link intraday prices to demand and supply fundamental factors. Or, of course, we are here surrounded by mathematicians, so it's also very common to employ purely stochastic models, ignoring the fundamentals. I hope at the end of my talk to form your own feeling which one would suit better when we talk about intraday prices. So some stylized facts, I'm sorry for some of you, could be, oops, we have some extreme events happening, but in principle, I would like to motivate, to unify the knowledge. Why do we trade in the intraday market? I will mainly refer to the German market in this talk and in this first part. So we need the intraday market essentially to correct positions that we took in the day-ahead market. For instance, we observe here on the graph, in the day-ahead market, let's say we purchase or sell a certain amount of power, for a certain hour delivery period, being 1 whole hour. That happens in the day ahead And when I place my position in the day ahead, basically I have in mind expectations. Expectation of my demand, expectation of my weather and renewables coming into the system. We, however, know that this is not a spot, but it's a day ahead market. So a lot can happen. There's a lot of uncertainty, there are a lot of major forecasting errors in the weather. And therefore, what essentially happens, if we talk here about the delivery period as being a morning hour, we have the sun ramping up effect, right? So we know that at the beginning of that delivery period, the photovoltaic in feed is lower than the average plant for that hour. And because the sun goes up continuously in the morning, at the end, at the fourth quarter of that hour, we actually have more photovoltaic in feed than the average of that hour. So what essentially happens in these 15-minute quarter-hourly products in the intraday market, we balance quarter-hour ramps with quarter-hour contracts. Here I offer you some examples. So what sort of corrections, who needs these corrections, right? We talk about, for example, if we are a renewable energy producer, we have to react to changes in forecasts. I will show you in a while my model. Then we deal, of course, often with power plant outages, optimization of power plant usage if we are a generator, have a generator, or optimization of demand if we talk about the consumer. And after this very general slide, I would like to move on. And I picked up for you some stylized facts, again, from the intraday prices for 15-minute quarter-hourly products on the German market. We show you here an average over the intraday prices observed between January and December 2015. We simply had a complete set of data we looked at. But the patterns, I can tell you, looking at one day recently, look very much the same. So what we observe, we distinguish between the peak hours, between 8 a.m. and 8 p.m. and the night. Because of what we have seen in the theoretical model before, this is already reflected in the pattern of prices. If we look at this sawtooth-like shape, this is actually very much connected to the photovoltaic in feed, for instance. At the beginning of the hour, because we have less photovoltaic in feed than expected, we are going to have a buy pressure, and then the price is at the highest. Whereas in the fourth quarter of that hour, we have sell pressure. There's more photovoltaic in feed than the average, so we have the lowest price. That's a pattern. So my colleagues who modeled so far this intraday markets without knowing this pattern might have been somehow tempted to believe that by storing electricity we can never explore such patterns, right? The problem is that, okay, this can be seen as a sort of time arbitrage, isn't it? If we know that the price follows exactly this pattern over the day, and surprisingly, it follows exactly the same sawtooth pattern in the night. So if during the day we can link this to the photovoltaic, what happens in the night? I cannot convince you of the same. So we had, when we presented this in front of the industry contacts, of course, we kindly asked them to reveal us a little bit what's going on. So while in academic papers we talk very much about market convention, use of private information, and so actually it's a bit more behind. It's also linked to fundamentals, but this time not to the solar, but it is linked to the design of conventional power plants. They ramp up and they ramp down, right, accordingly to less need for these conventional plants to run during the night. So the industry processes themselves, ramping down, ramping down profile, apparently cause at least part of this sawtooth-like shape. Okay, this given said, I would like to move on, and we can come back to this discussion, but very much linked to the price, we have the volumes of trades, right? So we have, I said, we have buy pressure at the beginning of each quarter of hour, which is reflected in the highest level of the volume of trades, and then we end up with the highest volume of trades in the last quarter of each hour, right? Because we have the sell pressure. So at the end, we have a pattern, and the pattern is a U shape. And here we prepare for you the time evolution of the number of trades, of course, on a very aggregate level, but these patterns are for sure recognizable also at 1 day level, for example. So why I chose to display this with just 3 hours before the gate closure? First of all, intraday market opens at 3 p.m. each day and ends with half an hour before the delivery period starts. It's a continuous trading, right? But the biggest fun happens actually the closer we come to the gate closure, and essentially within these 3 hours before the delivery period, we observe even 2 peaks. The closer we come, the 2 spectacular peaks, I'd say, are 30 minutes before the gate closure, and again the 1 minute before the gate closure. So this is called in commodity trading and modeling, and also financial stocks. This is the very well Samuelson effect in economics. That's what we observe as well in trading electricity, right? And I would like to come closer to understanding what causes these peaks in the volume of trades. So we motivated the need for intraday markets in order to balance out renewable energies. What does this mean? It means that the market participants, at least in Germany, I'm good aware that they have subscription to weather data providers, and during the continuous bidding process they follow up updated forecasting errors of weather. For example, updated forecasts of wind and solar for the wished delivery period they are bidding for. So we do observe here the evolution. We fix the delivery period. We look at, we want to forecast the wind for our first quarter of our 12, and this is for year 2015 as well. This is the evolution of the forecasting errors, updated forecasting errors of wind for this delivery period with exactly 1 day before the delivery, and we have 365 passes because we look effectively of all forecasts accounted for all days of 1 year. We observe also that the closer we come to delivery, the higher the uncertainty around the realized wind is. Why now? I've been surprised myself with my PhD student looking at this thing, not having so much experience and not having had the opportunity to talk directly to weather data providers. But it looks like the more in advance we do the forecast, they let some rough models run, and then the updates are done just at regular points in time, right? And the closer you come to the wished delivery day or wished forecasted period, the more often the updates are, because also the realized in-feed and the realized weather at that moment in time, let's say with some hours before the delivery, the forecasted period, they start counting very much. So if we believe that the intraday prices adapt to weather, then the uncertainty around this, the level of the price and so on should also reflect the uncertainty the closer we come to delivery. And now I propose you a sort of modeling approach in order to test. We had the privilege to get such a unique data set of updated forecasting errors, evolution of updated forecasting errors for wind and solar, and we want to see how market participants adjust their intraday prices in the continuous bidding as far as the new information is becoming available from the weather. And I will essentially refer to a bit older study of mine with Rüdiger Kiesel, 2017, and the newer one, again with Rüdiger and his PhD student, Marcel Kremer. And based on simply on examining the patterns, and we made some economical assumptions here. The first assumption of our model is that market participants adjust their prices in the intraday continuous bidding to forecasting errors of wind and photovoltaic as these become available from weather data providers. I must also tell you that they become available, they are updated each 15 minutes, whereas we have a continuous bidding in the intraday, so we had to map the information. And the second assumption, should we assume a sort of linear relationship, or do we have some asymmetric adjustment? And you will see in the results that actually it makes more sense to think in the following way. The speed of adjustment of the intraday price to updated forecasting errors basically depend on the gap between how much expected demand I had day ahead, and given this, how much expectation of renewables coming into the system I had. Given my expectation, the expected demand and the expectation of renewables, I plan the traditional capacity. So therefore, we believe that there are asymmetric adjustments depending on how much traditional plant capacity, speaking of Germany, coal, gas and oil and so on, depending on how much they plan the traditional capacity, this speed of adjustment can look differently. And therefore, we will employ a threshold model where the threshold variable will be exactly this gap measured in a measurement by the so-called demand quote. It's essentially demand forecast divided by power plant availability. As an information for you, expectation of renewables are fed with priority into the electricity grid. And the average expectation of renewables coming into the system is 20%. So in general, right? So our assumptions, we have, I prepared for you a toy example such that you can follow the story before I derive the mathematical formulas. So we have here the merit order of a in Germany, actually merit order curve. What does it mean? We have a demand quote at 1. It means that the traditional plant capacity for the day ahead covers fully the expected demand for electricity, and there is no or very low market expectation of renewables. And does this actually work? Yeah. And then, for example, for a demand quote of 1.2, it means I have a sort of expectation of renewables coming into the system, so I explicitly plan day ahead less traditional capacity, so that traditional plant capacity for the day ahead does not fully cover expected demand, right? So then I start having uncertainty. Will these expected renewables be really realized? Because we deal with forecasting errors, right? So the residual demand. And okay, if indeed the 20% renewables will be realized, we will have a decrease in the overall market price, obviously, and we will finally indeed close the gap. But if less photovoltaic and wind is coming into the system than expected, it means that we must bid for more expensive traditional capacity intraday, and this can become, of course, costly, which will put upwards pressure on the intraday prices. This is a little bit of theoretical assumptions we have made, and to estimate this model, we derived a story in a threshold model frame, employing as threshold variable the demand quote. And what we model here, we have changes in the intraday prices are a function of autoregressive terms going up to lag 3, and then we add negative or positive forecasting errors of wind and photovoltaic as they come as they become available, and then of course we correct with the demand quote. We include the volumes of trades, and because in the continuous bidding we have this challenge of modeling because the prices are not observed at equidistant points in times, right? So we deal with sort of arrivals and intensity of arrivals. Then we, by a crude approach, I'd say we have to take care by the last term of this pattern. So how my threshold is located, what is the level of the demand quote, which splits the story into regimes. I have no technical slides on that, but we use, for your information, Hansen's grid search. So the threshold is not artificially identified, but it is actually asymptotically derived by this procedure. And I know it's a little bit hard to follow, but I'm trying to pick up the most important results. The first result and the first question was how much do autoregressive terms count, and how much do we add if we take into account forecasting errors of wind and photovoltaic? So we deal, of course, with a huge amount of data and observations. If we take the evolution of prices for the various quarters, so the 4 quarters of our 12, we include or exclude the fundamentals. We observe that the explanatory power of the model doubles or triples if we include fundamental variables, so the forecasting errors from wind and photovoltaic. And when we apply the threshold model, essentially, something very interesting comes out. And the first interesting observation is that the threshold is located when the demand quote is 1.2, more or less. What does it mean, demand quote of 1.2? It means that there is a gap of about 20%, which is exactly the expectation for renewables in the market. So this is identified, it's not artificially created, and somehow it matches a bit with the pre-assumptions we had. On the other hand, what we observe, the coefficients or the adjustments, the coefficients showing a marginal effect of updated forecasting errors on prices, they become statistically significant, essentially, in that regime where the demand quote is larger than the threshold. What does this mean? It means that we kind of like are a little bit in trouble, a little bit in a hurry to close the gap, right? And therefore, the nervousness of the market participants in the continuous bidding increases because each update in the weather might create a sort of extra need to balance out, right? Especially given this pressure. Okay, so another interesting observation, if we look at the volume of trades, the coefficient of the volume of trades is positive in the first quarter of our 12, and it turns significant but negative in the in the fourth hour. And why is that? Well, it makes actually sense. In the first hour, in the first quarter, market participants need to increase the conventional output. We have a buy pressure, which increases prices. And then we have the sun ramping up effect. In the fourth quarter, we have sell pressure, which decreases prices. And now I will take my chance for the last remaining time, which is 5 minutes, I suppose. Okay.
You have about 5 to 10 minutes in this discussion.
Overall. Okay, thank you very much. Well, then I will tell you another story now. We will decouple a little bit from the fundamental modeling, but to conclude, to pre-conclude, so to say, based on this study, I would have two major conclusions that when we let run purely stochastic models, excluding demand-supply factors, we might lose significant explanatory power of that model. Because electricity pricing is very much, in my opinion, and in our insights, very much linked to demand-supply story. And the second one is that the adjustment okay, indeed, market participants in Germany in the intraday market really adjust and take into account the new information coming from the weather data providers. And in the research track on pricing and optimization of intraday, day ahead, and also futures markets, we had a very how can I say, interactive and insightful, and it has been a rich track actually, and several emerging, several research topics emerged, I'd say. You will also remark the interdisciplinarity in here, and I will talk not only about the intraday markets, but I will also tell you a little bit beyond that. So the first care, so to say, and the first research question that arose was actually, how do we deal with this Samuelson effect? Again, here we have the differences between the intraday prices and the day-ahead prices, aggregated over 6 years, such that you see a bit of a pattern on average, right? So it looks like when, and on the x-axis, you see how much time passed from the first bid that was placed, okay? So at the beginning, when the market opens, we see some nervousness there because we have already some outliers. But the closer we come to delivery, we really have an increased volatility. Again, together with Fred Espenbend, actually, we were wondering how to shape this. So if there was a emerging, how can I say, tendency or modeling approach in this track that was functional data analysis, namely identify the patterns and how can we mathematically shape the patterns. So first shaping them purely mathematically, and afterwards, if there's feasibility for that, add some demand-supply factors. And then we observe here, for example, a model for the volatility this time. Before, we have seen a model for the price level. Now we propose some modeling approaches for the volatility in the intraday prices. And then we can simply take into account by so the terms in the model. T0 is the time when we start, T is the time that passes, and T1 is the gate closure. So the three terms in here, basically one after the other, take care of the beginning of this trading period, and then allow for an exponential increase in the volatility the closer we come to the delivery period. Of course, this model, this is just the starting point, and we would like to extend the idea of that. Now, of course, such a model is not taking into account the fact that we have arrivals and that the intensity of trades is not equidistant in time, right? So another direction of thinking was to employ stochastic volatility models with time change, together with Julia Dinono and with Michael Schürle. And a lot of discussions were around how to apply and to extend the literature on random field modeling to energy data. So there are a lot of brainstorming sessions on that, and I would simply like to explain you first what a random field is very briefly to unify the knowledge. But before that, let's understand what's going on with this volatility in the intraday market. We observe here the evolution of the volatility of intraday hourly products in different years. And then we observe how the volatility, of course, plotted for each hour of the day. So this is time to maturity dimension, each hour of the day. And the time observation is with respect to the various years. And we observe that the volatility increased considerably over the years. And my colleagues, the mathematicians, seeing this graph, realized that the many random fields that have been applied to energy data aimed at examining the type of noise in electricity or energy term structures. Either that we talk about intraday term structure, meaning how is this process going from the first delivery period up to the last within one day as a spatial dimension, and how the information evolves over time. So we turn the thinking into terms of spatio-temporal dimension, and we aim at a joint modeling approach. And the nature of the noise have been found so far as being Gaussian, but in a excuse me, in a study applied to futures electricity markets, essentially the dW is not a VINA, but it is something else actually. So energy, for the colleagues passionate about random field models, the energy markets offer a variety of applications and possibility to extend the existing models to model random field models with stochastic volatility and random field models where the noise is not by far Gaussian. The non-Gaussianity of the noise in energy markets is definitely linked to the continuous increase in the renewable energies. And I have here a quick excursus. What's a random field, right? Because part of the research track has been focusing on that. So in a similar way, a random field looks very similar to a stochastic string model. Let's assume that the various lines could be price forward curves for electricity observed at different points in time, and along the curve we have the various maturity or delivery points, right? So basically in a Brownian field type of thinking, we assume that each point along the string is shocked arbitrarily by its own Brownian motion. right? But if we think in terms of random fields, we know that this stochastic string actually does never break apart, which means that the correlation between closer points can be really high, decaying fast the more distant the points are along the string. So in a similar way, we observe such fast decaying correlation patterns if we look at price workers for electricity. So essentially, a random field is distinguished by the spatial correlation structure of its increments. And a clear example in energy of random fields we propose already in some existing paper. And by the way, you know, I mentioned the move towards functional data analysis, which is a very trendy topic, very suitable to energy term structures, either that we talk about electricity or weather forecasts, right? Especially data allow us to identify the patterns, and with the functional data analysis, we propose a functional that simply shapes them. What we observe here is the volatility extracted along the term structure of futures. Okay, and then we observe the fast decaying volatility pattern in electricity future prices along time to maturity along the curves. And this is an example of functional data analysis. And to conclude, I have very, general messages to you. I wanted to keep my talk very general today. An important step towards, to conclude, an important step towards automatic trading is a careful selection of pricing models. First of all, fundamental variables matter, and we observe an adjustment of intraday prices to updated forecasting errors, weather forecasting errors, but this asymmetric adjustment of intraday prices to updated information on weather. The intensity of this link depends on the market expectation, the demand minus market expectation of renewables in the market. The location of the threshold, so we identify a threshold in the demand quote, in the so-called excess demand, right? How can we introduce such an information to optimize or to drive trading strategies? Well, this can be an indication, right? Can be used by market participants to adjust their bids accordingly and to move towards high-value trading by identification of trading strategies. And as a very general conclusion from our research track, mathematics helps shaping stylized facts. We move towards functional data analysis to shape, for example, volatility term structure, risk premia, noise distribution. And overall, our discussions really showed the need for interdisciplinarity for identifying realistic modeling approaches. So interdisciplinarity was really due for completion. Thank you very much.
Thank you. We have time for some questions.
Mine is not about the mathematics. It's simply because you have studied the German example. Can you give me some idea of the amount in kilojoules or gigajoules or whatever that the fluctuations on renewables have, as opposed to the fluctuations in demand? In other words, I'm saying to what extent are fluctuations in actual demand, how do they compare with the fluctuations?
I do not have the insight into how renewables can shift demand. Because if we have renewables in feed and ways of storing or using your own photovoltaic system, right, for your own use, you can kind of like shift somehow the demand. Probably your question goes into that direction, but my study did not really look into that. So I cannot answer directly your questions in quantitative terms. I'm sorry, but there is literature on that.
The statement was quite interesting that you made. The uncertainty grows closer to the time of delivery. Is that what you?
Yes, the predicted period. Yeah, if you refer to weather.
Is that because you're only allowing 15-minute updates to your weather forecast? Is that one of the reasons? continuous updates?
I see a colleague from whom I actually learned, Michael Coulon here. He's closer to such weather data providers, and what happens in reality, they use some models. If we are they start forecasting 8 days before a certain period, target period, right? And we observe a lot of stepwise, so nothing happens, no change in forecast over several hours, maybe also almost 1 day, at least in the first forecasting days. And what happens is apparently that they have some rough models, and they let them run just at periodic points in time. They are, I suppose they are, they do not link their forecast to realized weather, right, for that period, because they are still long in advance. But the closer to the targeted period they come, more feeling about what's the level of the wind now becomes, what's the level of the photovoltaic. So like now we are closer to the data, and we want to see, are these exploding updates in the forecast linked to the realized?
That's not the same as saying uncertainty grows. I mean, if so let's assume everything was Gaussian, and if I had to forecast something 10 days from now, I would probably have a larger variance about it. And if I was predicting something an hour from now, I would probably have a lower variance about it. And then my uncertainty is not growing. It's
yes, it was what I would have also expected. Yes, it is exactly what I would have expected as well. And what the first reaction of all colleagues who have a look at that graph is what's going on here. But the more we think, the more we realize that we call it uncertainty, right? Increased volatility in this weather forecast is exactly due to the fact that they update them on a more regular base, and they have more information to incorporate into it.
So is it due to the fact that you actually, like the uncertainty, it's like the effect on the price, you have the combined effect of like how much uncertainty is and how much effect it has on the price, so it must be decreasing uncertainty but faster than increasing effect on the price. Is that the reason?
I mean, it's only point forecast, yeah?
It's just a point
it's just
forecast,
a point forecast,
yeah.
But it's not published 8 days in advance. But the inaccuracy or the error of this forecast is, yeah? Of course, over time, the forecast gets in this respect more accurate, but simultaneously, it's also the expectation of this point forecast fluctuating simply more, yeah?
Yeah.
But you don't know in advance also the error
Exactly.
of some long-term forecast, yeah?
So if long-term in advance, I was quite far away of the truth, right? And then I update these models just randomly, so to say, I stay far away. But the closer I come to reality, we have a sudden increase or a sudden decrease, and therefore we have this volatility pattern in there. So that was my point. Yeah.
So I'm kind of questioning the value of this kind of a modeling approach, which is essentially detached from the physical characteristic, the network aspects, the basic fundamentals. For example, how do you study the German market? Can you tell me, based on this kind of a modeling, how the introduction, for example, of strategic reserve payments to lignite generator is going to affect all of that? I mean, what
very
part of the
hard
model is going to predict that?
Yeah. So such a model, of course, just partially answers some of our concerns, and we specifically wanted to have to answer the following question: do we have adjustment of intraday prices to new information coming up from the weather? So you refer to traditional plans, right? The problem is we have very little. It's very hard to answer such a question. Why? Because of a lack of granularity in the data available for the various plant capacity. We just have one number for the lignite plant capacity day ahead. And we try to get a sort of answer while looking at 15-minute products, right? So of course we have all the time constraints in our model and in their relevance, first of all, also by the data availability, one of the problems we have in here.
Isn't that one of the, like the wholesale prices in Germany have collapsed because of the introduction of all the wind, and the strategic reserve pricing have been tried to remedy that. So what can you help the regulator in their decision whether to introduce such pricing?
In a parallel model to this, we looked also at the influence of the reserves market and of the control area balances on the prices. And in our paper, you could see the speed of adjustment and quantify that as well. But not in what I showed today, because the message today was solely uncertainty from the weather incorporated in the price. And I'm also not, of course, we are not yet happy with the model because we did not disentangle, we did not take into account for the shape of the slope of the merit order curve. We simply stack all the technologies together. In this upcoming study, together with Rüdiger Kiesel, actually we are going to account for the slope of the merit order as well, because we believe that the speed of adjustment will depend in addition to the region of the slope, where the slope actually is, in addition to what we showed.
There are a few more questions,
Yeah.
I think. One
Yeah.
question here and one question there, and then we'll stop. Yeah.
I would like to know that also there are differences between energy markets. You mentioned Norway, which is traded manually, but what to balance there if it is hydropower mainly? And if you go to the south, you need much more volatility there. So I think when you are proposing model with autoregressive terms, you should probably vary it according to the market.
Very much. Yeah.
And Brownian noise should be varied according to at least weather products like Met-Office or ECMWF.
Absolutely.
So it should be kind of more general, probably, addressing the spectrum of European energy markets in different countries.
In this case, pure stochastic models are a better choice. But this is a more tailor-made, yeah.
So this is only Apex spot
Yes,
price.
yes.
If you have options around that, you would find out more, right?
For sure. So we could, for sure, yes. One could extend the analysis to that, yeah, as well. So I agree very much on the fact that electricity pricing should be very market specific. It's exactly how I started my talk. Yes.
It's a very interesting topic, but we
Yes,
have more.
yes, I think.
I'd like to thank the speaker again.
Thank you very much.